Contour integration. The integral is from 0 to infinity x to the power 4 over x to the power 6 minus 1 and dx. This is equal to pi over 2 root 3. So we will integrate our function fz to be equal to z to the power 4 over z to the power 6 minus 1. Just writing the function in terms of z along the contour C, which is indented at points. Just take the denominator equal to 0. So if z to the power 6 minus 1 is equal to 0, what points we can get on the real axis? We get -1 and 1 on the real axis. So at these 2 points, the contour is indented. If you look at this figure, this is point -1 and this is 1. So this contour is indented at -1 and at 1, having the semicircles as gamma 1 and gamma 2 with radius rho 1 and rho 2 respectively. And this contour is then along the real axis and followed by the semicircle tau, right? So we just need to write out the points first. This is -r and the contour starts from here. You can start from wherever you want to, but I'm going to start from here, from -r to this point. What is this point now? Because this is -1 and so this radius is also negative. So this point will be this -1 plus this negative rho 1 radius. So this point will become -1 minus rho 1. Just adding -1 and negative rho 1. And this point will be, this is from this -1, you are subtracting the radius negative rho 1. So that will be your rho 1 minus 1. So this point is rho 1 minus 1. Is this clear to you? See, because up to here, if suppose somewhere 0 is here, suppose, so this complete distance is -1. And I have to get this point. So for this point, I have to subtract this radius. And this radius is negative rho 1. So -1 minus rho 1. That will give you rho 1 minus 1. Is it fine? Alright. So what point is this now? This complete is 1. From here to here. This is 1. And this is 1 minus this rho 2. So this point will be 1 minus rho 2. And then this point will be, this is 1 plus rho 2. So we will integrate first along the real axis from -r to this point. And then we will integrate along this semicircle gamma 1. And then again along the real axis. And then again along the semicircle gamma 2, again then real axis, and then finally along the semicircle tau, right? So now the first step is to find out the poles of the function. To find out the poles of the function, how we find? We just take the denominator equal to 0, 0, and then this z power 6 is equal to 1. And I know that this 1 can be written as e to the power 2k pi iota. If you use your Euler's function, the result, Euler's formula, where k is integer. So this z is equal to, then take both the sides, 1 over 6 the power. So you get e to the power 2k pi iota over 6. Fine. So this is equal to e to the power k pi iota over 3, and this k will go from 0, 1, 2, 3, 4, 5. Why 5? Because I'm having the power as 6, so there must be 6 integers, right? Okay, if you put 0 over here, you get z is equal to, yes, 1. Okay, then you put if 1 over here, you get e the power pi iota over 3. If you put 2 over here, you get 2 pi iota over 3. That is, then if you put 4 over here, you get e the power 4 pi iota over 3. And then like so on. Just put the values of k one by one over here to get the points. So the poles of the fz are at the points. First, if you put k equal to 0, you get 1. Then if you put k equal to 1, you get e the power pi iota over 3. And then you get e the power 2 pi iota over 3. Sorry. Then you get e the power 3 pi iota over 3. That will be e the power pi iota, that is negative 1. This e the power pi iota is negative 1 because e the power iota x is cos of x plus iota sine of x. If you put that value, so you will get from the Euler's formula as e the power pi iota equal to negative 1. Then is e the power 4 pi iota over 3. And finally e the power 5 pi iota over 3. Now if you look at these poles, already 1 and negative 1, at these 2 points the contour is indented, right? So the remaining poles are first, second, third, fourth and fifth. So out of these 4 poles, half of the poles lie inside the contour. So only first 2 poles lie inside the contour. So we will find the residue at these 2 poles only. So the poles lie inside the C is e the power pi iota over 3 and z is equal to e the power 2 pi iota over 3. Now to find out the residue at these 2 poles, we will calculate the residue of fz at alpha, suppose. So if I calculate the residue at alpha, then that will be equal to, what is the formula? Just write the numerator as it is and then derivate the denominator with respect to z. This is the formula for finding the residue at z equal to alpha. So this is equal to z the power 4 over, this is 6 z the power 5 at z is equal to alpha, and you will get at last 1 over 6 z. So 1 over 6 z, z equal to alpha, which means I get 1 over 6 alpha. Right? So in place of alpha, I will put first pole and then the second pole, and then I calculate the sum of the residues at these poles. So the sum of the residues at first this pole and this pole is equal to, just put this value at here alpha, so I get let me take 1 by 6 outside. So I'm putting the value of alpha first, this e the power pi iota over 3, and then putting the value of alpha as e the power 2 pi iota over 3 because I'm adding the residues now. So this is equal to, just take the LCM and you will get e the power 2 pi iota over 3 plus e the power pi iota over 3 over e the power pi iota over 3 e the power 2 pi iota over 3. And then this is 1 over 6. Now I know that e the power 2 pi iota over 3 is equal to, see, this is cos of x plus iota sine of x, where x is 2 pi by 3. So this is equal to, what is cos 2 pi by 3? This is, yes, negative 1 by 2, very good. And then plus iota, what is sine 2 pi by 3? It is root 3 by 2, alright. So this is how we can find the value. So this value is negative half plus iota root 3 by 2. And similarly, just find e the power pi iota by 3. What is cos pi by 3? It is 1 by 2 plus iota times sine pi by 3 is root 3 by 2. Simple, alright. So if you add these two powers, you get e the power pi iota, which is simply negative 1. So I get minus 1 over 6 because of this e the power pi iota. I get negative sign here. Half is cancelled with this and you get twice of root 3 by 2 iota, which is root 3 iota. Right? Now I am going to use the Cauchy's residue theorem, which is integral over complete contour C f z dz is equal to 2 pi iota times the sum of the residues. And sum of the residues we have calculated as negative root 3 iota over 6. So iota becomes iota square, and that is negative 1. So this will become now positive, and this 2 will be cancelled with the 6. So I get now pi over, pi root 3 over 3, which is also equal to pi over root 3. Just rationalize, you get pi by root 3. Fine. Now splitting this contour into so many integrals, because we need to integrate along the x-axis and also along the semicircles, then the big semicircle tau, right? So taking first integral from negative r to minus 1 minus rho 1 along the x-axis, and then integrating along gamma 1 semicircle, and then along the again x-axis, and then along gamma 2, then again x-axis, then along the tau. This I know that always equals to 0. It always comes out to be 0, and this whole sum is equal to pi over root 3. So this is pi over root 3. So first, I just need to calculate this thing and this thing. Rest of the integrals will be merged from negative infinity to positive infinity along the real axis. So calculating this as limit rho 1 tends to 0. Please remember, whenever you integrate along the semicircles, the smaller ones where you are indenting the contour, for that the radius always tends to 0, and for tau the radius always tends to infinity. Please remember this. So the radius rho 1 is tending to 0. Integral over gamma 1 fz dz is equal to, the formula is iota 0 minus pi. Remember this, iota 0 minus pi, limit z tends to negative 1, because my semicircle gamma 1 is indented at point z equal to negative 1. So limit z tends to negative 1, z minus this negative 1. So that will be z plus 1, right, into f of z. So this is equal to, this is negative pi iota, limit z tends to negative 1. This is z plus 1, and the function is z the power 4 over z the power 6 minus 1. This can be break up into z cube minus 1 and z cube plus 1. So this is minus pi iota limit z tends to negative 1. This is z plus 1, z the power 4. Now again, I know that this can further be breaked up as, this is z cube minus 1. Further I can write z cube plus 1 as z plus 1, then z square plus 1 minus z, the formula. And these two are cancelled out. And now if I put the value z as negative 1 here, I will get my final answer to be equal to pi iota over 6. Okay. So next, second, limit this second one. Rho 2 tends to 0 along the second semicircle, integral gamma 2 fz dz equal to iota 0 minus pi, limit z tends to 1, because the contour is indented at 1 for this semicircle gamma 2. So limit z tends to 1, z minus z naught is 1, so this is z minus 1, f of z. So this is negative pi iota limit z tends to 1, z minus 1, z the power, it is 4 over z power 6 minus 1, which can again be splitted up as z cube minus 1 and z cube plus 1. Now because now I am having z minus 1 in the numerator, so I need to now split this, which is z minus 1, the factors, and it is z square plus 1 plus z, and this is z cube plus 1. Just cancel these two, and putting the value of 1 over here, you get the value of z as 1, then you get minus pi iota. Just put 1 over here, you get 1 over 6, so which is equal to minus pi iota over 6. And finally, along the tau, so limit r tends to infinity. Now here you have to take the radius tending to infinity. R tends to infinity along tau fz dz equal to iota 0 minus pi, same formula, but limit z tends to 0 always. And z minus z naught, because z is tending to 0, so here is z minus 0 f of z. Fine. So this is equal to minus pi iota limit z is tending to 0. This is z into z power, this is, the function is z the power 4 over z the power 6 minus 1. Sorry, this is z is tending to infinity. I'm so sorry. Z is tending to infinity. So this is equal to, this is z the power 5, and in the denominator I'm having the higher power. So of course, z is tending to infinity. This will comes out to be 0. If you take z the power 5 common, you get 1 over from here. If you take z power 5 common, so this is 1 over z minus 1 over z the power 5. So if you now put the value as z tending to infinity, you get the answer as 0, because 1 by infinity this is 0, and 1 over infinity this is 0, complete. So this answer comes out to be 0. Now letting rho 1 tends to 0, rho 2 tends to 0, and r tends to infinity in 1. The first equation is this. The main equation, this equation as 1. Now when you put r is tending to infinity, you get negative infinity 2, because rho 1 is 0, so negative infinity 2 minus 1. And then putting the value over here, we have just calculated for gamma 1, and then this will be from -1 to 1 because rho 1 and rho 2 are tending to 0. Then put the value of here into this integral value we have calculated, and then from here I get from limits are from 1 to infinity because rho 2 is 0, and then this integral is always coming out to be 0. So I'm just putting the values. So I get the integral as -infinity to -1 fx dx. Then the integral second for gamma 1, the value is pi iota over 6. And then the integral is along x-axis from -1 to 1 f of x dx. And then minus pi iota over 6, the value for the integral having semicircle gamma 2. And then the integration 1 to infinity f of x dx, and then for gamma that integral is 0, so this is equal to pi over √3. So I'm merging this together, so I get from -infinity to infinity, and these two are cancelled, so I get this as pi over √3, right? And what is the value of fx? It is -infinity to infinity. Now fx is x to the power 4 over x to the power 6 minus 1 dx is equal to pi over √3. Now because this is my even function, so this integral will become from 0 to infinity twice. Sorry, I'm writing over here. So from 0 to infinity twice x to the power 4 over x to the power 6 minus 1 dx is equal to pi over √3. Fine. And finally I can get from 0 to infinity, my final result is now, I get, as you take this 2 to the other side, you get pi over 2√3 as your final, the required result. So here ends up the proof. Thank you so much for watching this video. God bless you all. Goodbye.